All right, Gary. Well, first off, this I think the theme of this is distances, explaining the effect of the distances between the screen and whatnot. And I think I can do that because I support this. Just explaining physics to ourselves. I think we should be able to do that. Look, we did that with Newtonian physics. We did it with the Earth moving around the sun, and we can do it with this. And it's just by being brave. And all the people that are like, no, don't think about it. Only a scientist can think about it. You and I can join together and saying, fuck that. Okay. And I did overstep, or not overstep, but whatever. I maybe misrepresented even a little. And I got to it later. But yeah, later in your video, uh, made it clear that with detectors you were talking about the crystals. But I mentioned the crystals, so I answered that. So enough about that. Um, I mean, I'd apologize more, but you're rude to me in like every other video of yours, or a little bit in everyone, and I don't mind it, whatever. Or I do mind it, but then you go right back to talking about what we're talking about, and that's what's important to me. Okay. The thing is, the video I showed you, and this is where my frustration comes from, and where my short temper or whatever comes from about it, is that it's not you're not a skeptic, and I'm not telling you to shut up at all. I'm encouraging you to talk about it, um, but you're ignoring evidence as far as I can see. And I understand that maybe from your point of view, you're not ignoring it. You're just hey, I'm not accepting it wholeheartedly because I'm skeptical about it. Fine. But come on, the video I gave, it was mostly lame, true. But I took 30 seconds to find something with apparatus in it. Okay, with a picture of the apparatus working right there, and it showed you the screen, and it's the CCD, and that's what they use. And what would you expect if they use photographic paper? They have used it, but it's like, what, you're going to put up one thing and then shoot one photon, and you're going to get thousands of dots that way. And what is that going to prove? Because people have done limited amount of stuff like that, but really, why? In the photographic paper, the photon, alters the chemical and makes it turn into a dye. That's not actually superior to a CCD, which, pretty much literally just collects photons. Like you said, they could be called a collector, but they do call those detectors. Okay. And in fact, if you want to get all technical, and I don't mean technical as scientists talk, but I mean in just our regular human language, that is a kind of a detector. And we're really talking about, yeah, a collector might be distinct from a sensor, possibly. And I said in the video that, yeah, the photon, something happens to the photon. And it's obviously that we do influence it because it takes away the interference pattern. But it's funny when you imply that having the crystal there would make it all scatter all over, because what happens is, instead of the multiple lines of an interference pattern, you just get the really regular two particle oriented ones. So yeah, I'm going to talk about the distance. The distance is definitely, I'm going to tell you how the distances affect everything, and the reason that it's not generally brought up. Um, Hopefully you'll get my explanation of that. I'll try to make that clear. Um, you complain that he doesn't show the defects after it builds up. I don't know what you expect if they extended the time lapse. I mean, you've seen a lot of the ones. If you extend the time lapse, you get so many dots that they don't look like dots. It starts to become a smooth picture, just like with pixels. If you have enough dots, it starts to look smooth. So it just smooths it out. I mean, so showing that is just showing it where you can still see, the effects of individual photons. Um, you know, um, I'm sorry, but uh, I don't mean it as an insult, but I do think you're confused about photons. I think we're all a little confused, and scientists in there said it was hard. So yeah, that's fine, but it doesn't mean I'm not going to use the word confused, or when I think I'm confused. Maybe you were confused on that particular thing. So whatever. I already told you what makes me short-tempered in this is that, look, there's the apparatus, and you're still going to go, why won't they show us? Piro's just saying You know, I don't need to give you I mean, I took 30 seconds and took the first thing that showed an apparatus. I wasn't even willing to look at the video all the way through to make sure. Okay, so, um, I did end up watching it all the way through. I didn't care if it was lame or had a lame host. It shows an apparatus hooked straight to a CCD to a camera. You can see it operating. There you go. If it's grainy and you don't like that, fine, that's what it is. You want it smoother, if you run it longer, it'll be smoother. You know, anyway. We talked about the time lapse and the photographic paper. I don't know what you think that would show. Um, Regulating when they show up. Well, actually, you kind of caught me on misusing the term laser. Obviously, a laser doesn't do one photon at a time because it's a collimated beam, which implies a whole bunch of light that's collimated, and it's multiple photons. And then really, what we're talking about is single photon light sources. But yeah, you can't regulate when they show up. Statistically, a certain amount are going to show up in a certain period of time, but you don't know when the next one's going to come. And you saw that in that apparatus. It's like ting, 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 ting. Okay. Right. Dimensions. Okay. The basic thing is this. We're saying that this is a wave, right? So here is a diagram of waves, right? This is a wave front, right? So right over here, this part here, this is the wave front. It's parallel, and the wave is confusing. Is going this way. And there's the little slit. You can see the little slit right there. And basically, after it hits the slit, it makes these circle patterns mathematically. Now, mind you, it'll really be a cone. It's hard to line up with that thing. Going out, masked off a little bit. But they do always start to spread out again, and basically, it's like this circular shape. Okay. So the crofts go out here, but they start to fade out, sort of like a rainbow. Theoretically, the whole arc is there because when the water, if it was a water wave, the water's going up and down right at the slit. So, it pumps a little wave off to the side, too. But it's fainter than the wave that goes straight ahead. So there's a circle there, mathematically or in principle. But in reality, it fades out, and who knows, by here it might not really seem much. Okay? Now, when you have two slits, then you have that pattern overlap. That's kind of the point, right? This is the point. Now, look, it does matter. The distance between the slits, super important. It has to be, it's important whether or not it's a multiple of the wavelength. The width of the slit, also super important. If a slit is a mile long, and a wave with the wavelength of an inch goes through it, it's not affected. For a mile long slit to affect the wave would have to be a mile long. They're intimately connected, the size of the slit. And you try to make a really sharp slit like razors, coming down to molecular if you could, okay? But the main issue is that it's a really good mask, and it matters because of, the Maxwell's wave equations, what the width of that slit is. And it's called diffraction. Refraction is when waves go through, change substances. They go through an interface in crystals. Okay, so that's refraction. And when particles do something like refraction, it doesn't look like a refraction phenomena. It's a kind of scattering. Now, light can also be scattered, but it's a kind of scattering when, as a particle, something is split off in an essentially random or somewhat random direction. I say somewhat random because scattering implies random direction, but you can get, regularized polarity and other things. So, it's a filtering like everything. But partly it introduces an unpredictability, or it's used when there's an unpredictability to deal with. Not that you can't make it a predictability. Okay. So if you see here, it's very important where, how big each slit is, because that affects, it transforms the size of the slit. If it doesn't match the wavelength, then there's a transformation. The wave is transformed differently. So they perform this with waves and slits that are of comparable sizes. And the slits are the same size. Why? So you get an interference pattern. If you do it irregular, the pattern's still there, but it gets blurred out, so it's out of focus, and it just looks like a pattern. Okay? But you can see from this what happens if you move these slits farther apart. Right? What happens? The circle patterns go further apart, and they still have the crissy-crossy, but where the crissy-crossy changes. So, for example, I'm not trying to be condescending. I'm sorry about that. Okay, see, you have like these little radial patterns, right? Okay, look, we'll draw lines where these things overlap and where the troughs and crests meet. Okay, so look, this is a trough. I mean, this is a crest. This is the top of the wave, these lines. Could be either way, but this is the top of the lines. So look down here. This is the top of the green. Where this blue and that green go, that's this line here. These red lines are where the tops meet. That's where you're going to get a white dot. Okay? But wait a second. We haven't just put up a screen yet. This is spraying off into space. The blue lines are where a crest meets a trough, the bottom. Okay, see, this is where the green is in the middle of two blue. So that's where you get dark spots. So see, look, moving around the distances of this stuff, it's pretty clear what happens. You get a moire kind of, if you know what that kind of thing is, pattern where this overlap moves around. It's still an overlap, okay? If you move it in units of the wavelength, then the pattern actually looks pretty similar, but it'll be fainter in the middle if they get really far apart, but the bars will be a similar kind of thing. If you do it in units of that, because they'll cross over the troughs, it'll be a similarity. Okay, and where you put the screen says where you're going to get your dots. So if I put the screen out, well, let's see, let's do something flatter. Okay, so let's say I put the screen right here, then that's where the dots are going to appear. If I put them up here, the dots will, the bars rather, excuse me, will be up closer. The dark spots will be closer together. It's just, that's a linear relationship. These lines have, I keep doing it the wrong way, but these lines have angles. And, that's not, people don't talk about it that much because that's just the mathematical part. No matter where you put the screen, you get an interference pattern. It looks a little bit different. There's a geometric spreading. The further away the screen is, the farther the bars are apart. I mean, you're not surprised by that. This is the geometry that answers that, I think. I know you understand all that stuff really well, actually. And as I said, and I mean this as a compliment, I'm reading this book. I don't try to tell people to read books, but turns out, people ask me what to read to understand this stuff. Biography of Einstein. So it goes into this guy's life, but it talks about what he went through, with the various steps and why they believed in particles or didn't believe in particles or continuity. All of these things we're talking about exactly. And also, by the way, a lot of his papers, the seminal ones, very accessible. You just read his paper on special relativity. Read his early paper on Brownian motion. It was 100 years ago. You'd be surprised how understandable it is. And the guy didn't even like to use very much mathematics. He didn't really use mathematics in those papers. Until general relativity, he wasn't a fan. He thought math was a luxury. Okay, so those early papers are surprisingly readable. He wasn't in the scientific establishment. He was working in the patent office, free thinker. He just knew ways to think about physics in interesting ways. And there's good arguments there. And he ended up concluding some things that he didn't really particularly, he thought there should be a continuity. He didn't like quanta. Okay. So I don't think anybody's keeping the key information from you, because really it's a lot of information, but there's a lot per hour too. I mean, it really is not like, well, you have to be indoctrinated. No, it's like physics classes. We're talking about a physics degree, but they have online physics lectures. They have, the papers of Einstein, which I'm arguing are more accessible than people might think, the original ones. General relativity and tensor math gets, forget it, but MIT has curricula online. They probably have some physics curricula. There is this key information, things that like how far do we put the screen away? See, people don't talk about that because that's not the interesting part. If you see that diagram, you see how far away, that's just going to change the geometric cross section you take of this